Good morning, dear guests and conference participants. We are pleased to present to you at the Water Management and Environmental Engineering workshop our report on intensify agricultural production by means of thermal reclamation. The authors on the report are presented on the slide. Research on this issue has been carried out by us since the year 2004 and has been going on for more than 10 years. These presentations show the results of one of the most representative agroclimatic conditions of the year.
The problem of getting early and permanent yields of agricultural crops, particularly vegetables and berries. Flowers of saleable quality is one of the major socio-economic issues in agriculture of many countries. Studying the influence of possible climatic and weather changes on the development and productivity of agricultural crops production and development measures to prevent the negative climatic and weather phenomena are becoming relevant in agriculture not only for researchers but also for professional practitioners. Thermal resources play a significant role in yield formation. Each plant has its own strictly individual thermal temporal structure of the development cycle from sowing to harvesting. The parameters of the cycle are strictly related to the corresponding level of temperatures in the soil and air. Therefore, purposeful control of plant ontogenesis can be possible by controlling the thermal regime of the microenvironment of its habitat. It is obvious that the thermal regime of the soil and the surface layer of air will be also decisive for the intensification of processes of growth and early cultivation of crops. The task of heat supply for crop production in the early spring periods is traditionally solved by creating greenhouse facilities and by heating the soil. Thus, high-temperature sources of thermal energy are used for heating the soil and air in cultivation facilities, which are obtained by burning high-value fuels, primarily natural gas. Significant increase in the price of natural fuels and thermal energy puts on the agenda the tasks of finding, justifying, and developing alternative ways to regulate the thermal regime of the soil and air, sources of alternative energy with the purpose of getting early harvests of agricultural crops. One option for solving this problem can be creation of soil areas heated by special thermal reclamation facilities using thermal waste from industry. Hot water, heat exchange water, from industrial and power generating facilities with a temperature of 20-40 degrees and geothermal water can be used as attractive free sources of thermal energy. Their attractiveness is that such temperatures are optimal for the development of most crops. One of the promising and effective methods of thermal reclamation of adjacent areas, in our view, can be the surface heating of soil with warm water with the temperature parameters within 25-35 degrees. The working scientific hypothesis is that the maximum thermal effects when using water with such temperatures should be expected with directing the water flows to the area of plant's habitat. The transfer of thermal resource in the amount of 15-20 degrees to the environment soil layer will theoretically allow shifting the transition through 10 degrees to the end of February, beginning of March. Technologically, this technique can be implemented by directing the water flow in a thin layer of the soil surface and can be technically executed with the application of special sleeves, heat exchangers of various designs and geometry made of thin, long-lasting, flexible polymeric materials, films. The thermal efficiency of soil heating with water-filled flexible sleeves was studied experimentally in a field model experiment performed in the climatic terms of Ukrainian Polissya on sandy loam and chernozem soils. Strawberry of the Festivalny type was used as the main crop indicator. The soil was heated with specifically heated warm water, which circulated by gravity flow under a small initial pressure, 10 to 20 centimeters. centimeters. The temperature of water in the sleeves was automatically maintained with 24-26 degrees in March, with a subsequent increase in April and May up to 27-30 degrees Celsius. The temperature of the soil, air and water circulating in heat exchangers was measured by precise meteorological mercury thermometers, window thermometers, to the depths of 20 centimeters by bird thermometers in depths, electric thermometers, and aspiration spectrometers. In the experiment, part of the heated adjacent areas was additionally protected by a tunnel-type film greenhouse. For this purpose, polyethylene film with the thickness of 150 micrometers was used. The water was heated by an automatic water heating device. The heated water supply was regulated by dampers and valves. The initial states of soil heating by heat exchangers was started by us since 12th of March 2009 during 2 weeks. All parameters were measured twice a day at 7 o'clock a.m. and 7 o'clock p.m. The basic results of measuring the temperature of soil, water and air are shown in Figure 3. An open heated ground in natural conditions was taken as a control option. The research results show that surface heating is an effective technical method of thermal reclamation of the plant's habitat, which makes it possible to quickly and reliably increase the temperature of the soil and the surface air when using a film cover. On the third day of operation of heat exchangers, the temperature in the upper 20 cm soil layer rose to 10-14 degrees of Celsius. At the same time, due to the heat flow of the surface of heat exchangers upwards, the surface air layer warmed up to 8-11 degrees. On the 4th-5th day of the heating system operation, favorable temperature conditions were created at the level of 14-16 degrees of Celsius in the upper 20 cm layer of soil and about 10-12 degrees in the surface layer of air, which were constantly preserved even on cloudy and frosty days. Therefore, heating with heat exchangers, which is very important, is guaranteed to maintain the positive air temperature at night and protect plants from frost. The soil's temperatures obtained as a result of constant heating, 14-16 degrees of Celsius, promotes the germination and development of most vegetable and berry crops, even thermophilic ones. In the case, under natural conditions, soil and air temperature remain very low, varying from -2 degrees of Celsius to 3 degrees of Celsius. The whole period of observations of the soil in natural conditions remained unprepared for agricultural use due to low temperatures. Great importance in assessing the temperature of the heated soil is attached to the peculiarities of its formation during the vegetation period, March to May, as well as during the day. According to the results of our research in 2013 conducted on sandy loam soils of the Ukrainian Polissya, the influence of the surface heating is more noticeable in cold periods, March-April. In the course of our research, it is found out that the general nature of temperature changes during the day. Both in the heating section and in the control one, it remains the same. For example, the maximum temperatures of soil and the depths of 5 cm for the heated area are reached at 4 p.m., 6 p.m. and are within 27-29 degrees of Celsius, while the control area at 5 to 6 p.m. reaching the temperature 18-19 degrees. The minimum soil temperatures are observed in the heated area at 7 o'clock, 8 o'clock a.m. and are 19-20 degrees, and in the control areas they reach 12-13 degrees at the same time. The process of heat exchange in the soil air systems and the direction of heat flows depend on the thermal gradient conditions in the soil. The heated soil is characterized by the presence of maximum temperatures in the area where heat exchangers are located, surface soil. Therefore, the dynamics of margin gradients and their type of movement must be investigated for a considerable soil layer. In March of 2009, soil temperature at the depths of 0 to 12 centimeters in the control area was below zero, while in the heated area it reached 11 to 13 degrees of Celsius. In the layer from 20 to 80 centimeters, the temperature of control soil changed from 0.5 degrees Celsius to 3.5 degrees Celsius, and in the heated area area, it ranged from 8 degrees of Celsius to 11 degrees. A completely different picture is observed in May. For example, the soil layer ranging from 0 to 20 centimeters in the control areas, the temperature is 20-21 degrees Celsius, and in the heating area, 31 to 34 degrees Celsius. In the layer from 20 to 80 centimeters in the control areas, soil temperature is 16 to 20 degrees Celsius, and in the heating area, 26 to 32 degrees Celsius. The difference in sums of soil temperatures at the depths of 20 centimeters as compared to control area are more than 2000 degrees Celsius. As our research has shown for the heated soils, the relationship between the moment that determines the beginning and suspension of active vegetation of plants is the date of transition of air and soil temperature through 10 degrees of Celsius. With the onset of the dates of temperature transition through 10 degrees Celsius, the same patterns appear along with the beginning of active temperatures period. In the area of heating by heat exchangers, the date of temperature transition through 10 degrees Celsius in the soil at the depths of 20 centimeters in 2009 fell on the 1st of April, and in the control area on 22nd of April, that is 21 days earlier. We studied the effect of surface heating on the growth and development of the Festivalny strawberry type. The results of observation during March to May 2000 Field research has shown that heating of soil with heat exchangers circulating hot water with a temperature of 25 to 30 degrees of Celsius increases the temperature of the arable layer by 12 to 16 degrees Celsius in the soil and by 7 to 12 degrees Celsius in the air, which provides sufficient conditions for plant growth and development in early spring. It is proved that heat with heat exchangers allows the period of active soil use to start earlier in the spring by 40-60 days for sheltered soil and also increases the amount of positive temperatures in the arable soil layer during the spring period by 1500 to 2000 degrees Celsius. Close linear relationships are established